All right, let's put on our detective hats. Today, we're cracking the case of those sneaky hidden zeros in polynomials. We're going to break this whole thing down into a master workflow that you can use to find every single zero every single time. I guarantee it. So here's the mystery we're tackling. You've got a polynomial, right? And its degree is supposed to tell you exactly how many solutions there are. But sometimes you go looking and you can only find one. Where did the others go? Well, they're the elusive, irrational, and imaginary zeros, and today we're gonna hunt them down. Here's our game plan. First, we'll learn the rules of engagement. Then, I'll show you the master workflow. After that, we'll put it to the test and crack 3 different cases. I'll show you how to avoid the common traps, and finally, we'll see why any of this actually matters in the real world.
Okay, let's dive right in. Every good detective has to know the law, and for us, in the world of algebra, there are 2 theorems that are basically the laws of the land. You absolutely have to know these.
First up is the big one, the fundamental theorem of algebra. Think of this as a promise. If you have a polynomial with a degree of, say, 3, this theorem guarantees you that there are exactly 3 zeros. Not 2, not 4, 3. This is awesome because it tells us exactly when our job is done. Now for our first huge clue, the complex conjugate pairs theorem. This basically tells us that imaginary zeros are never loners. If you find one, like a plus bi, you've automatically found its partner, a minus bi. They're a package deal, always. And that, my friends, is a massive shortcut in our investigation. So now that we have the rules down, it's time for the secret weapon. This is our master workflow, a reliable step-by-step process that takes all the guesswork out of finding zeros. It turns a chaotic search into a clear, methodical hunt. And here it is. Step 1, we use the rational root theorem to line up all our potential suspects. Step 2, we interrogate them using a slick technique called synthetic division. Every time we find a zero that works, we get to reduce the polynomial's degree, which makes our problem way simpler. We just repeat that process until we're left with a basic quadratic equation, which we can always crack with a good old quadratic formula. All right, enough talk. It's time to see this thing in action. We're going to apply this workflow to 3 different cases, from a nice, straightforward one to a polynomial hiding those really tricky, irrational, and imaginary zeros. Our first case is a classic. It's a cubic polynomial, and all its zeros are nice, clean, rational numbers. This is the perfect warm-up to see just how powerful and efficient our workflow is. We'll test one of our candidates, x equals -1, using synthetic division. Watch this. We bring down the coefficients, then we multiply and add all the way across. And look at that. The last number, our remainder, is a big fat 0. That confirms -1 is a 0. But just as important, look at these new numbers. Those are the coefficients of our new, simpler polynomial. And just like that, we've broken down that complicated cubic into a simple quadratic, x squared plus x minus 6. That's a piece of cake to factor into x plus 3 and x minus 2. And boom, there are our last 2 zeros. We've found all 3, case closed. Okay, for case number 2, things get a little more interesting. I have a feeling some of these zeros aren't going to be nice, simple integers. Let's see how the workflow handles the hunt for those hidden irrational numbers. So, we test a few candidates, and it turns out x equals 1 is a winner. We run it through synthetic division, and once again, we get a remainder of 0. Perfect. We found our first 0, and we're left with a new quadratic to solve, x squared minus 2x minus 4. Now, this quadratic, x squared minus 2x minus 4, it doesn't really factor nicely. But that's no problem at all for our workflow. We just pull out the big guns, the quadratic formula, and it spits out the 2 hidden irrational zeros, 1 plus the square root of 5 and 1 minus the square root of 5. Done. And now for our final case. This is the one that really stumps people. We're hunting for the zeros of a polynomial that's hiding an imaginary pair. This is where knowing about those conjugate pairs is really going to pay off. So we can attack this by factoring by grouping, or we can just test our rational roots and find that x equals 1 is a 0. Either way, we end up with this expression, x squared plus 4. When we set that to 0, we get x squared equals -4. And when we take the square root of a negative number, we get our 2 imaginary zeros, 2i and its conjugate partner, -2i, exactly like the theorem said we would. So you've seen the workflow in action. But hey, even the best detectives can fall into a trap. Let's go over a couple of common mistakes so you can make sure your investigations are always successful. This is probably the biggest pitfall right here. Someone finds one real root for a degree 3 polynomial and they just stop. They close the case. But they're forgetting the promise from the fundamental theorem. It guarantees 3 zeros. If you've only found one, you have to keep digging for that hidden complex conjugate pair.
So why on earth do we spend all this time hunting for these numbers? Is it just a math exercise? No way. Let's look at a real-world application where this exact skill is absolutely critical: electrical engineering. You see, when electrical engineers design a circuit, they actually create a polynomial. They call it a characteristic equation that describes it. And finding the zeros of that equation isn't for a grade. It's fundamental. Those zeros literally predict exactly how the circuit will behave in the real world. And this is the payoff. This is so cool. Real zeros. They correspond to stable, predictable behavior, like the smooth power coming from your phone charger. But complex zeros, that means you've got oscillations, the very thing that creates radio waves, audio signals, and all sorts of vibrations. The type of zero directly predicts the physical behavior. Is this powerful, direct link between abstract algebra and the technology that literally powers our lives? So we've seen that with the right method, even the most hidden mathematical secrets can be brought to light. You now have a master workflow for finding polynomial zeros, so the question I'll leave you with is this: what other elegant, hidden rules are just out there, waiting for a good detective like you to come find them?